Hello, my dear students. So, welcome to my YouTube channel. So, this video is for Karnataka CET NEET classes, where I'll going to upload some important points chapter wise. Where, for example, if I take a solid state, so as you all know, the weightage is around 2 to 3 questions. So, now in a short time, instead of studying or instead of going with the entire chapter, if you go through some important points, then it will be very helpful and it will going to save your time. Okay, so with that point of view, here are some points that you had to go through. Okay, so now I have taken a solid state, so the weightage is around 2 to 3 questions. Okay, so let us start with, and here I have included some points through which you may get the questions. Okay, so let us start with that. So the first point here, you could see solids have a definite mass, volume, and the shape. So that's a basic property that we know. So in case of a solid state, when it comes to a different like states of a matter, solid state is one in which how we're going to categorize, how we're going to characterize the solid state. So they're having a definite mass, volume, and the shape. Okay, and they have intermolecular distance a very short, means they have a very less intermolecular space. Okay, and the intermolecular forces are strong since they are present, since they are compactly arranged, since the intermolecular space is very less. Obviously the intermolecular force of attraction will be very high or very strong. Okay, so their constituent particles like atoms, molecules, or the ions have a fixed position and they can oscillate only at their mean position, obviously. So when they are in a compact arrangement, when they can't change their place because of the high force of attraction, they can oscillate only in their mean position. Okay, they cannot change their position. Okay, so that's one property. And when it comes to kinetic energy, they have a very low kinetic energy because of the arrangement. Okay, so now they are incompressible and rigid. Yeah, as we all know, they are tightly packed, they are compactly packed. Okay, they are in a regular arrangement. So if you try to compress by applying a pressure, you can't compress those solids, and they are rigid in nature. Okay, then crystalline solids are anisotropic in nature. So what do you mean by anisotropic? Means, so when we study the properties, physical properties like a refractive index and all, so when you study the same property in a different direction for the crystalline solids, so in a different direction we will going to get a different values for the same property. Okay, that means what? If I'm studying the refractive index, okay, for one crystalline solid, I'm going to study with a different direction. Okay, so when I go with a one direction, okay, what happens? The value we're going to get, let us take it as a x. Okay, when I go with another direction, let us take a value we're going to get will be y. Okay, so what happens? I'm studying the same property over there, but what is happening? We are getting a different values. So that is called anisotropic in nature. Okay, so now amorphous solids are isotropic in nature. Yes. Okay, so why? Because in case of a what I can say, in case of a amorphous solids, you cannot predict the exact arrangement. Okay, so you cannot predict the exact arrangement over there to a longer distance. So what happens? When I try to study the same property in a different direction, I may get the same value. Okay, so that's why they are known as what, dear students? Isotropic in nature. Okay, so now let us come to the type of a crystalline solid. See, based on the constituent particles. Okay, based on the constituent particles, the crystalline solids are divided into molecular solids, okay, ionic solids. Okay, next comes a covalent solids, metallic solids. Okay, let us go with that. Let us go with the molecular solids. So what are molecular solids? So as the basic classification is based on the constituent particles. So in case of a molecular solids, the constituent particles are molecules. Okay, so when it comes to ionic solids, okay, the constituent particles are ions. Okay, so in the properties that if we need to study the bonding and the attractive forces, it might be an electrostatic force of attraction, or I could say an ionic bond. Okay, and electrical conductivity, insulator in a solid state. So this point you have to concentrate, dear students. They are insulator in a solid state. Okay, but they're going to conduct in the molten state or in aqueous solution. Obviously, when they comes in aqueous condition, obviously they turn into an ions. Okay, so ions are responsible for the conductivity, but when they are present in a solid state, okay, they are like they will going to act as a insulator. So do concentrate on this point. Okay, when it comes to physical nature, yes, they are hard and brittle in nature. Okay, so that you have to concentrate. Okay, so let us move to the next point over next what I can say, the points that melting point. Okay, when it comes to ionic solids, its melting point is very high. Okay, and the point that you have to remember over here is examples. So dear students, you have to concentrate on examples. So which are the example for the ionic solids? Calcium fluoride, zinc sulfate, MgO and NaCl. So these are the examples for the ionic solids. Okay, they may ask you based on examples also. That point you have to concentrate. So now let us move to the next type of a solids, that is metallic solids. Okay, so when it comes to a metallic solid, so when I say metals, as we all know, they are the good conductor. Okay, so what are the constituent particles in case of a metallic solids? We have a positive ions in the sea of a delocalized electron. Okay, there is a presence of free electrons in a metallic solids. Okay, and the bond that we're going to see is a metallic bond, and the conductivity, they are the good conductor in solid state as well as in a molten state. Why? Because of the presence of delocalized electrons. Okay. Now, when it comes to a physical nature, they are hard, but they can be malleable and they can be ductile. Means we can, by applying a pressure, we can turn them into a what again say thin wire as well as a thin sheet. Okay, melting point, it's fairly high because of the presence of a metallic bond. And the examples: iron, copper, silver, magnesium. Okay, so you can give a many examples of for the metallic solids. Okay, now the next type of crystalline solids is covalent or the network solids, dear students. Okay, so when it comes to covalent or the network solids, the constituent particles are atoms. Okay, and the bonding is covalent bond you could observe. Okay, so not the strong bond. So electrical conductivity, yes, they can be a conductor in solid state as well as in a molten state. When it comes to physical nature, they are hard but malleable in the ductile, and the melting point is fairly high. Okay, so obviously because of the presence of a strong bond, examples: SiO2, that is quartz. Okay, silicon carbide, carbon, diamond, carbon, a graphite. Okay, so these are example for the network or covalent solids. Okay, after this introduction point, we need to go for the unit cell. Okay, what are unit cell? Unit cell are nothing but a building blocks for the entire crystal system. Okay, when I consider a building, the bricks are the what I can say, the bricks are the fundamental part for the entire building. If you want to construct a building, the bricks are very important. So when I repeat those bricks in a regular manner, okay, in an arranged manner, what I can see or I can construct the entire three-dimensional building, dear students. Okay, the same thing will going to happen over here. So here the unit cells are the smallest repeating particles, I could say, okay, which when repeated over and over again generates the complete crystal lattice. Okay, so it consists of an infinite number of unit cells. Okay, and where the question you can get over here, dear students, so these are the questions from which, like these are the 7 crystal system from which you can get the question. Okay, so what are those 7 crystal system? So the 7 crystal system, the first one is a cubic, and I have given one video. Okay, so how to remember all these 7 crystal system, basic 7 crystal system. Okay, cubic, tetragonal, orthorhombic, monoclinic, hexagonal, and the next video I'll going to give you. Okay, so what happens, they will going to ask you the questions based on this one. Okay, so they're going to give these arrangement, and they're going to give 4 options, out of which type of a crystal system, okay, will going to give these parameters. Okay, so For this also I have given a video. You can go through that one. Okay, I'll going to give a link in the description box. Okay, and even they will going to ask you the examples. Okay, what are the example for the cubic, tetragonal, orthorhombic? That also have given an easy way to remember the examples. Okay, so that we will go through. Now let us move to the next. That is, so in the 7 crystal system, here you could see rhombohedral or trigonal and triclinic. Okay, yes. Now come to a type of a unit cell. So type of a unit cell, primitive or simple unit cell consisting of a particles only at the corners. Okay, so face centered, they consists of constituent particles at the corners as well as at each face. Okay, when it comes to a body centered unit cell, it consists of a one constituent particles at the body center and the atoms at the corners. Okay, so when it comes to end centered, it consists of a one constituent particles present at the center of any 2 opposite faces, dear students, in addition to the corners. Okay, yes. Come to next point, number of atoms in different unit cells. So this you have to concentrate. Either based on this one, they're going to ask you a question. So number of atoms in primitive unit cell is 1. Okay, so contribution of those atoms which are present at the corner is 1/8. Okay, it comes to a face center, how many number of atoms or the rank of a unit cell is how much? 4, and the contribution of a face atom is half, that is 1/2. When it comes to a body center, the rank of the unit cell or the number of atoms will be 2. Okay, so this you have to remember. Now come to a coordination number. It is nothing but the number of nearest neighbors of a particle or the number of atoms in contact with each other. Okay, so now here there is an arrangement of a, what I can say, the unit cell. Okay, so based on the arrangement of a unit cell in a 1 dimension, 2 dimension, 3 dimension, you could explain the close packed structure. So here also you may get the question based on the like coordination number. Okay, so here the 1 dimensional close packing of a sphere. Okay, so for this 1 dimensional close packing sphere, what is the coordination number? See, this 1 atom is in contact with how many atom? Here 1, here 1. So the coordination number is how much? 2. Okay, this you have to remember. Now close packing in 2 dimensions. So in 2 dimension, I can arrange the constituent particles or the spheres. Okay, so here it is generated by stacking the rows of close packed spheres in a 2 ways. So close packing in 2 dimension can be done in 2 ways. One is square close packing, one is hexagonal close packing. Okay, so now what do you mean by square close packing? What do you mean by hexagonal packing? Means here you could see, just a minute. Yes, so here you could see, dear students. So in case of a 2 dimensional square close packing, what you could see, this is what the arrangement. Okay, so this is square close packing of spheres in a 2 dimension. So how they are arranged, you could see here how they have arranged A type. Okay, this arrangement also they're going to ask you. Okay, and when you want to count the coordination number, this 1 atom is in touch with how many atoms? This one, this one, this one, this one. That is 4. So coordination number is 4 for what? Square close packing in a 2 dimension. Which type? The arrangement A type arrangement. Okay, so this is where I have given. Okay, so that 2 dimensional square close, 2 dimensional close packing can also be done in a hexagonal close packing. Okay, so how? It is of the type AB. Okay, which type of arrangement? AB type of arrangement, and the coordination number is this 1 atom is in touch with how many? 6 atoms. Okay, so the coordination number is 6. Okay, so these points you have to remember. You will get the question based on this one. Okay, so this is about the 2 dimension. So when it comes to 3 dimensional close packing from 2 dimensional square close packed structure is here. Okay, 3 dimensionally in all the 3 axes, I can repeat the constituent particles or the spheres, that too in a different way. Okay, so here you could see 3 dimensional close packing from the 2 dimensional hexagonal close packed structure. Okay, dear students. So by taking this hexagonal close packed structure, I can arrange that in a three-dimensional way. How? Here are the two possibilities. Placing these bond layer over the first layer, placing the third layer over the second layer. Okay, so here, so three-dimensional close packing from the two-dimensional square close packing. Okay, so which type? AAA type of arrangement, and that will going to generate what? That will going to generate a simple cubic cell with a coordination number 6. These points you have to remember. Okay, yes. So now, so this one possibility, as I told, one possibility is this one, that is I'm going to take a square close packing of a 2-dimension and I'm going to repeat that in a 3-dimensional way, that is like a AAA type arrangement. Okay, what it will going to generate? It will going to generate a simple cubic cell. Okay, which type of arrangement? AAA type arrangement. What is the coordination number? Coordination number is 6. For what the coordination number is 6? For the simple cubic unit cell, the coordination number is 6. Okay, so there is another way of arrangement, that see here. Hexagonal close packing. Okay, 2-dimensional hexagonal close packing is taken and that is repeated in a 3-dimensional way. Which type of arrangement, dear students? AB, AB, AB type of arrangement. So when I arrange this in a AB, AB type of like arrangement, okay, what it will going to generate? It will going to generate hexagonal close packed structure. Which hexagonal close packed structure? It is 3-dimensional HCP. Okay, so what is the coordination number? 12. This you have to remember. Okay, which type of arrangement? That is ABAB type of arrangement. What is the structure it is generating? It is generating HCP. Okay, so HCP in 2-dimensional have a coordination number 6. HCP in 3-dimensional have a coordination number 12. That's the difference you should remember. Okay, now comes to ABC type of arrangement. So that hexagonal close packing structure can be done in another way. That is ABC type arrangement. Okay, that generates what? The FCC unit cell. Okay, so coordination number of that FCC unit cell is 12. So how this arrangement can be done? For this also I have done a video. Okay, so by taking one live example, okay, I have uploaded an video. Okay, you can go through that one. I'm going to mention in the description box as well. Okay, now come to a type of a voids. Okay, so there are two type of, what do you mean by voids? So when we arrange these constraint particles, I could see some interstitial site or void or space over here. That what we're going to call it as a void or interstitial site. So there are two types of void. One is tetrahedral void, one is octahedral void. Okay, so how octahedral void is formed? It is formed by the center when 6 pairs are joined in the form of an octahedron. Okay, so how tetrahedral void is formed? So the 3 atoms above which another atom is kept over here. That results in the formation of a shape of a tetrahedron. Okay, and how we are going to find out? There is a relation between these two. See, if the number of close packed particles are n, okay, in that one, number of particles present in octahedral void will be n. Means if the number of atoms is n, the number of octahedral void is n. The number of tetrahedral voids will be 2n. So you have to remember this formula. Okay, now come to packing efficiency. So it is a percentage of total space occupied by a constraint particles. Okay, so in a crystalline solid, how tightly, how closely, what percentage of a total space will be occupied by the constraint particles. So has got a formula: packing efficiency, volume occupied by the sphere by the total volume of the unit cell into 100. Okay, so here I have not given that derivation. I have directly given packing efficiency of a face-centered unit cell is 74%. See, out of like 100% space available, 74% space is occupied by the constraint particles. So what is the free space available? How are you going to find out the free space? 100 minus 74. That gives a free space in a face-centered unit cell. So packing efficiency of a BCC is 68%. Packing efficiency of a simple 52.4. Okay, and this you have to remember, radius ratio in an octahedral void. For an atom to occupy an octahedral void, its radius must be 0.414 times the radius of the sphere. So this point just add on. Okay, so now radius ratio for the tetrahedral void. This is for the octahedral void, and for the tetrahedral void, for an atom to occupy a tetrahedral void, its radius must be 0.225 times the radius of the sphere. Okay, so the radius ratio R divided by R is equal to 0.225. So you have to remember this formula. Now come to density of a unit cell is same as the density of the substance. Okay, there occurs a formula to find out the density of the different type of a unit cell. For that, I have given a shortcut way how to calculate in a shorter time. That I am going to mention in the description box. Now, relationship between the radius of a constrained particles and the edge length. This is very, 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 very important because the question will appear from this part. Okay, simple unit cell consists of a relation A is equal to 2R. A is an edge length, R is radius. So for the simple, A is equal to 2R. Okay, for the face centered, A is equal to 2 root 2R. For the body center, A is equal to 4R by root 3. Okay, what is the volume of a unit cell? Length into breadth into height, that is A cube. Okay, so simple cubic unit cell volume is equal to, that is 2R cube. For the face centered unit cell, volume is equal to 2 root 2R whole cube, because here the A value we have taken. Okay, for the body centered unit cell, volume is equal to 4R by root 3 whole cube. So the number of atoms in a unit cell, which I have already told. Okay, so again I'll going to repeat that. Hold on for a minute. Yes. So in case of a simple unit cell, Z equal to 1, that's the rank of the unit cell also you can say. For the face centered, Z equal to 4. For the body center, Z equal to 2. To find out the density of a unit cell, D is equal to Zm by A cube into Na. Okay, Z is the rank of the unit cell, M is molecular mass, A cube is volume of the unit cell, Na is Avogadro number. Okay, next point is any departure from the perfectly ordered arrangement of atoms or the ions in a crystals is called imperfection. Okay, so there is a regular arrangement of the atoms. If an atom or the line of an atom is removed, that causes the imperfection or defect. So there are two types basically, point defect, line defect. Okay, so you have only the point defect over here. So in that one, Schottky defect is very important. You are going to get a question based on this one, that is Schottky defect. How it occurs? It occurs, this is very important, when a pair of ions of an opposite charge, that is a cation and anion, are missing from the ideal lattice. Okay, the presence of a large number of Schottky defect lowers the density of the crystal. This is very important. Example, silver bromide is the one. Okay, now come to next one. Atoms or the ions which occupy the normally vacant interstitial sites in a crystal are known as interstitials. It results in the increase in the density of the crystal. Okay, Frankel defect. This is another type of a defect. Okay, it is a combination of a Schottky defect and interstitial defect. That means it's a combination of a vacancy defect as well as interstitial defect. It occurs when an ion leaves its position in the lattice and occupies an interstitial site, leaving the gap in the crystal. So the density will not going to decrease, density remains same. Okay, so when it comes to a non-stoichiometric defect, it's a large number of inorganic solids in which the ratio of the number of atoms of one kind to the number of atoms of the other kind does not correspond to the ideal whole number ratio. Such compounds are known as the non-stoichiometric compounds. Okay, when there is an excess of metal ions in a non-stoichiometric compounds, the crystal lattice have a vacant anionic site. Okay, these sites are occupied by electrons. Okay, and those electrons are called as a, means those space which are occupied by the electrons are called as a F center, and those F center are responsible for the color of that compound. Okay, so based on their electrical conductivity, solids are classified as a conductor, insulator, and the semiconductor. Okay, pure substance that show conductivity behavior like that of a silicon and germanium are called intrinsic semiconductor. When solid substances are placed in a magnetic field, they do not show the same behavior. Depending on their response to a magnetic field, the substances are classified as diamagnetic, okay, paramagnetic, okay, ferromagnetic, ferrimagnetic, antiferromagnetic. Okay, in case of a diamagnetic, these substances are weakly repelled by the magnetic field. Okay, the electrons are paired here. Paramagnetic, these substances are weakly attracted by the magnetic, and it consists of a unpaired electrons over there. Substances having the unpaired electrons are classified as ferromagnetic, antiferromagnetic, and ferrimagnetic. So based on this arrangement also, they may ask you the question. Ferromagnetic, all the electron will be aligning in one direction. Okay, antiferromagnetic, here you could see, ferrimagnetic, here you could see. So this is some information regarding the solid state. So whatever the points you have learned, okay, till now that you are studying for the solid state, okay, so you can add on these points within a short time. You can complete more information. Okay, so this is about what I can say, the solid state. Like this, I'm going to upload some more videos of an important topic. Okay, thank you so much.